Okay, so in this lecture we prove the primary decomposition theorem. Okay. So we have the primary decomposition theorem. Okay, let's see. So what was the statement of the primary decomposition theorem? So what was the statement of it? So let V be a finite dimensional vector space, right? Let V be a finite dimensional vector space over a field F. Let T be a linear operator defined on V. Let small p be the minimal polynomial of T, and small p is given as p1 to the power r1, p2 to the power r2 till some pk to the power rk, where each pi are monic irreducible polynomials over f. Okay, they're monic irreducible polynomials over f, where each ri is a positive integer. Okay. Let w1, w2 till wk be the null space of each of these PIRIs. Be the null space of each of the operators P1 to the power R1 of T, P2 to the power R2 of T, and so on till Pk to the power Rk of T respectively. Okay. Then we have the following. Then number 1, V is given as W1, direct sum W2, direct sum W3, so on and so forth till Wk. Number 2, we have each Wi is T invariant. Each Wi is T invariant. And number 3, we have that if we denote Ti to be the restriction of T on these Wi's, for all I obviously, then Pi to the power Ri is the minimum polynomial of Ti. Okay, so this is the primary decomposition theorem. Okay, let us come to the proof of it. The proof of it. What is the first thing we do? The first thing we do is that we show that there are k projection operators on V such that the identity operator can be written as a sum of these operators. We show that there exists k projection operators E1, E2 till Ek such that I can be written as E1 plus E2 so on till Ek. Okay, on V. Okay, and the range of Ei is Wi, because in the previous theorem we have dealt with such conditions, because this will immediately say that V is a direct sum of each of these Wi's. Okay, so let us do that to be very precise. Now we are given that the minimal polynomial P is of this form, right? So it's P1 to the power R1, P2 to the power R2, so on till Pk to the power Rk. We choose a polynomial f such that Fi is given as P upon Pi to the power Ri. Okay, for all I equals to 1 to k. then by the way fi is chosen, it's obvious that we are just removing the each of these factors from p1 from p, and having this each of the polynomials f1 f2 till fk, then obviously none of these fi's will have a common factor, right? Therefore the gcd of these fi's must be equal to 1. But if so, then we can have polynomials g1 till gk such that the linear combination of g1 gi with fi's give you the value 1. Then there exists k projection operator. This is a classical result from number theory, right? There exists k projection of there exist k polynomials. There exists k polynomials such that k polynomials g1 g2 till gk such that g1 f1 plus g2 f2 and so on till gk fk is equal to 1, right? We choose hi to be the polynomial gi fi for all I is equals to 1 to k. Therefore the sum of these hi's, so h1 plus h2 till hk is 1, right? But then what happens if I use them as operators? So h1 of t, h2 of t, hk of t, it's simply 1 of t, that is the identity operator, right? Right? Okay. So this is, suppose say this is statement 1. Okay, suppose this is statement 1. Now is each hi a projection operator? Is each hi a projection operator? How can we answer this question? Okay, so for I not equal to j, okay, for I not equal to j, what is hi hj or hj hj, whatever? So it's fj gj times fi hi, okay? But that implies that p must divide hj hi, right? Because p will divide this term. Since these are polynomials over a field, so obviously they will commute, right? Now, if they commute, then you get the value fj fi as a collective term. But the way fi fj are individually constructed, p must always divide the function fj fi. So that is typically speaking, p must divide hj hi, right? So if p divides hj hi, then that typically means hjt times hit must be 0 because p is the minimal polynomial. So p will annihilate the operator t, right? Why does this happen? This happens as p of t is 0, right? But if hjt hit is 0 for all I not equal to j, and we also have that I is written as h1t plus h2t and so on plus hkt, then these two statements eventually conclude the fact that hj squared t is same as hjt for all j equals to 1 to k, which implies hit is a projection operator, for all i's running from 1 to k. Clear? Clear? So we have successfully proved that there exist projection operators such that the identity operator can be written as the sum of them, and the range of so there exist projection operators, k projection operators such that the identity can be written as sum of them, right? So let hit be the operator ei. In the previous lecture we had also proved the fact that in such a case these ei's are polynomials in t, so it's kind of relevant, right? Okay. Next we claim that Next we claim that the range of each of these EIs is Wi. Okay. Wi is given to be the null space of Pi to the power Ri. Right. So we prove this. So we choose an element from the range, let's say. Let alpha be an element from range of EI. But range of EI is nothing but Hi of t. Right? Right? EI is obviously a projection operator. So that means alpha can be written as Hi of t alpha. Right? This was a condition, a characterization of the range of a projection operator. So alpha is equals to Hi of t alpha. Right? But then what can we say about Pj? Sorry, what can we say about Pi to the power Ri of alpha? So it's Pi to the power Ri t. Sorry, we need a t here because we are acting them as operators. So Pi Ri t times Hit of alpha. So both of these are polynomials over t, so they will again commute, right? So we can write it as Hit times Pi Rit of alpha, right? Or we exactly don't need this to be very precise, because observe that the way Hi is constructed. So how is Hi constructed? So this is typically of the form Pi Rit. What is Hi? Hi is Fit Git alpha. How was Fi constructed? Fi was constructed to be P upon Pi to the power Ri. Therefore that implies P must divide Pi Rit, or rather, let me not use the term T here because we are now acting as polynomials. So P must divide Pi to the power Ri times Figi, which implies P must divide Pi to the power Ri Hi. But P is the minimal polynomial for T. So that means Pi Ri Hi of T must be equal to 0. Right? Right? Therefore, so Pi Ri of T of alpha is 0. So that implies alpha must be in the null space of Pi to the power Ri of T, and that is exactly given to be Wi. Right? So we have shown that the range of EI is contained in Wi. Okay. We need to show the inclusion from the other side. Okay. So we try to do that. Now let us choose an element from Wi. Let alpha be an element from Wi. So that again means that Pj Rj of T of alpha must be 0 by definition of Wj. Okay. Right. But from here what we can conclude? So if Pj Rj of T of alpha is equal to 0, then that immediately means that Hj of T is, sorry, if this is equal to 0, what we can say is that, let us just think of it. If this becomes 0, what can we say about the polynomial h? See, we need to show that alpha is in the range of EI, right? And range of EI is typically the range of Hi of T. Or in this case, let us choose J. Yeah, we have chosen the index to be J. So we have to show this, right? Okay. Now, yeah, observe that what is H, how is Hj chosen? It is Fjgj, right? What is Fj? Fj is P upon Pj to the power Rj. So if I choose this function h with an index other than j, that is if we do the same for some index I, let's say. Okay. If I choose this for an index I, so if I do it for hi is equal to fi times gi, and fi is p upon pi to the power ri, then it is obvious that for all I not equal to j, pj to the power rj will obviously divide hi, right? Because it will divide fi, right? because we are just cancelling out the pi to the power ri factor from p. So for I not equal to j, the pj to the power rj factor is still in p, right? Therefore this will divide p, and other way around it will divide h. Right? So that implies for all I not equal to j, hit of alpha must be equal to 0, right? But how can we write alpha? But alpha can be written as h1t of alpha plus h2t of alpha and so on till hkt of alpha. Why is it so? Since the identity operator is the sum of these operators. So it's h1t plus h2t and so on till hkt. Further, we have hi of t of alpha to be equal to 0 for all I not equal to j. So that immediately implies that hj of t of alpha must be equal to alpha, and that proves that alpha must be in the range of hj of t, which is basically range of ej. So we started with an element from wj, we ended up showing that the element is in range of ej. Therefore wj is a subset of range of ej. So I guess I named the previous statement to be statement 1, right? Oh, this was in this lecture. I just boxed it. Yeah, so suppose this is 1 and suppose this is 2. I guess it's clear from here. Therefore from 1 and 2, range of ej is equal to wj, and this happens for all j, right? So we have already proven that these wj's are direct sums, or v is a direct sum of all these wj's, because we have k linear operators which are projection operators, and identity can be written as identity can be written as e1 plus e2 till e, right? So this was this was a theorem which we had proved in the invariant direct sum cases, or rather in the direct sum decomposition cases where we had discussed about projection operators. Like this thing was done there, right? Is it clear? So what are we left to show? We are left to show that each of these wj's are t invariant. Okay. So we have two things left. One, to show that each of these wi's are t invariant, and next to show that the minimal polynomial of wi, sorry, the minimal polynomial of t restricted to wi is pi to the power ri. Okay. First we show that to show each wi is t invariant, right? But since wi is the range of ei, this was a lemma we had dealt in the previous lecture, I guess, but we had showed that it's enough to show that t commutes with ei, right? And this is obvious, right? Since ei is nothing but hi of t, therefore t of hi of t must be equals to hit times t, as hit is a polynomial in t, right? And this happens for all I is equals to 1 to k. That immediately implies that range of ei, which is equals to wi, is t invariant for all I is equals to 1 to, right? So we are only left to show that if I restrict t to the subspace wi, then the minimal polynomial of ti is pi to the power r. Okay. So okay, one more thing to observe directly from here is that since each wi is t invariant, therefore we can write t as t1 plus t2 till tk. This was also something which we have dealt in the previous 1 or 2 lectures, where ti is the restriction of t to wi, right? This we have dealt. Okay. Clear. So we are left to show that the minimal polynomial of Ti is Pi to the power R. Okay. How do we show this? Okay. What we do is that observe that Pj Rj of T, this is equal to 0, right? Because P has distinct irreducible, monic irreducible factors of Pj to the power Rj form, right? But T can be decomposed in this form, right? And Pj to the power Rj, it typically acts on Wj. So that typically implies Pj to the power Rj of Tj is equals to 0. Therefore, if T is the minimal polynomial of, because what is Wi? Wi is typically the null space of Pi to the power Ri, right? That's the basic fact which we are using here. So if T is the minimal polynomial of Tj, then small t must divide Pj to the power Rj, right? This is the first thing. Suppose this is 1. Oh no, we had used 1 and 2, right? So suppose this is 3. Okay. Now, what can you say about T of Fj? What will T of Fj do? Now, T of Fj is a polynomial such that T of capital T times Fj of capital T must be equal to 0. Clearly because small t is a minimal polynomial. Right? Now, we have that for all vectors alpha in V, alpha can be written as h1t of alpha plus h2t of alpha and so on till hkt of alpha. Why is it so? Since I can be written as h1t plus h2t and so on till hkt. Clear? Suppose we choose hit to be alpha I as a component. Sorry, hit of we can choose hit of alpha to be alpha 1, alpha I. So let hit of alpha to be alpha I. Then clearly alpha I is annihilated by Pi to the power Rit and alpha j by small t. But I and j are arbitrary index, right? Therefore, P must divide T of T times Fj. But that means, because P is the minimal polynomial of T, right? P is the minimal polynomial of T. Since Pi to the power Ri capital T, this annihilates alpha I, and small t annihilates alpha j. Small t capital T annihilates alpha j. So small t times Fj must annihilate. So P must divide small t times Fj, because how was Fj defined? It was defined as P by Pi Ri, right? Sorry, Pi to the power R, like this. So is this clear? But if P divides this, then obviously we can write P from this expression as Pj to the power Rj times Fj dividing T of Fj. That clearly implies that Pj to the power Rj must divide T. So if this is statement 4, then 3 and 4 implies that T must be exactly equal to Pj to the power Rj. Right? Now this was what we have to prove. Right? Yeah, so we have proved the primary decomposition theorem, and we are kind of completed the part of elementary canonical forms, typically from the book Hoffman-Kunz. From the next lecture onward, we will be studying the concepts of cyclic subspaces. Okay. So meet you guys in the next lecture.